All right, here's the lesson 3.45 combo lesson. So we're using, it's actually just a single lesson, but we're going over a couple things from both in the book 3.4 and 3.5. So we'll call it kind of a combo 3.4, 3.5 notes, slopes, graphs, equations, and lines. So this is a break in concepts as far as we've been doing a lot of geometric proofs, 3.1 through 3.3, proving lines parallel, proving angles congruent or supplementary. Kind of connecting some of those concepts back to some of our algebra roots. So we're still talking about parallel and perpendicular lines, but putting them now in the context of a coordinate plane is basically what's going on here. So we'll go back, we'll review some stuff as far as slopes and equations of lines. How do I write equations of lines? And how does that, how do parallel and perpendicular lines relate on the coordinate plane? So let's jump in, let's get it going. We'll actually start with a 3.4, 3.5 kind of prerequisite skills check. These are skills that you learned in algebra class that we need to be able to do to have some success here in the current lesson. So there's nothing here geometric. I really just want to make sure that we can that we're able to do some of the skills. So I'm just getting a little bit of space to work here. But the setup for each one is the same. Write an equation of the line in slope-intercept form, okay? So the first thing there, and we'll kind of do some notes even on here. So slope-intercept form, hopefully we recall, is the form y equals mx plus b. That should be something that you're very familiar with, covered extensively in Algebra 1, where m represents our slope, and b is our y-intercept, which would be the point 0, b, right? And then x and y just represent all the other points that fall on that line. So that's the equation of a line. That's slope-intercept form, y equals mx plus b. So what I'm basically asking us to do here for a, b, and c, it's the same question everywhere. It's the same direction, I guess, every time. Write an equation of the line in slope-intercept form that has these criteria, has these characteristics. So the line that for the part A has to have a slope of 3/4 and pass through the point 0.8. So this is about as easy as we're ever going to see, as far as, and I mean easy in that we have all the information we need. All right, to write something in this form, I need a slope, which we're seeing right here. Hey, we have a slope, and we need a y-intercept, which we have the y-intercept. Every y-intercept has this in common, that it's the point 0 something, 0, -8. So for part A, there's really no work beyond identifying, hey, I have a slope, I have a y-intercept, I can jump right to this y equals mx plus b form and fill in everything I know. So y equals m, which we're now replacing with 3/4, because that's what it said our line has to have, a slope of 3/4, 3/4 x plus b. So I would probably write it as -8, or you could write it as plus -8. That's that. So we're kind of easing into it here, hopefully a little bit. That, all right, that's not that bad. If I get the y-intercept, now that's extremely convenient. That's one specific point, 0, -8. Most of the time, which we'll see here in the next couple examples, we don't get that point, or we don't know that point. We actually have to kind of figure it out. So let's move on to part B here. So I'm going to kind of scroll. Hopefully we have the stuff written down already. The next one is asking us to, same direction, write equation in slope-intercept form that has this criteria, that has a slope of, now it's small there, but -1/2, and passes through the point 22, -1. So on the surface, it almost looks identical. Like, oh, sweet, hey, I have a slope, I have a point. But now this point right here, 22, -1, that's nowhere near the y-axis. 22, -1 is way off in quadrant 4. I'm not saying there's any element that you should be graphing here, but at least we should see, hey, this is the y-axis. 22, -1. 22, -1 would be hanging out way over here, depending on what your scales are. So that's not on the y-axis. 0, -8 in the previous problem was right on the y-axis. That's why we could use that as our y-intercept. So we need a different game plan here, which brings up the next form. So we've talked slope-intercept form, really nice, y equals mx plus b. The next form that we're going to use here, and for the majority of our problems that we're going to use, is this form. It's called point slope form. So this would be something that we need to add to our notes. Point slope form, we're kind of doing a prerequisite skills check and a notes all in one here, a review notes session. Point slope form looks like this: y minus y1 equals m times x minus x1. And this, again, should be something that you were at least exposed to in an algebra class. All sorts of stuff going on there as far as y's and m's and x's. The m still is m. Like, m is still our slope. That's going to be unchanged. M still stands for slope, which for us, hey, we have that. We have m. That's awesome. Where this form is going to be a little bit more useful than the y equals mx plus b, though, is this x1 and this y1. So the point x1, y1 just represent any point. So I'm trying to leave space to work here, but that point x1, y1 represents any point on the line that we're talking about, which, again, we have. This is a random point, 22, -1. It's not the y-intercept. So we know m, we know x1 and y1. What's going on with this other x and this x and this y? Those are just going to be there. Just like we saw up above here, when we write an equation of a line, there's always just like a generic y and there's always a generic x. Those represent all the other points that are on that line. So it's the same thing going on here. There's just a generic x and there's a generic y. We don't do anything with them. All right. So this is the form we've got to be able to use. We don't have to memorize it. I'll provide it to you on a sheet of paper when we do or I'll put it on the board when we do a quiz or a test. But for right now in our notes, I would think this is something we definitely need to add, and we got to go through this example. So how do we do this? How do we use this? Well, we kind of just talk through it, but m, right, that's my m. And then this, if it's helpful, which I think hopefully it is, we'll call this x1 and this y1 because that's the x coordinate and that's the y coordinate. So why not call it x1 and y1? And we basically fill in everything we know in this form right here. So y minus, let's see, that's a minus, like the minus is right here. And then my y1 is -1. So I got to be careful. We've seen this with distance formula, subtracting negative numbers. Y minus y1 equals m. We said our m was -1/2. I don't want to lose that little negative there. It's pretty small. -1/2 parenthesis x minus x1, which is 22. All right, we said x2 is 22. And you're saying, well, what the heck? This seems so weird. This isn't slope-intercept form, and you're 100% right. It's point-slope form. That's why we called it point-slope form. But if I can get all this stuff where it goes, this slope where it goes, my point where it goes, I can basically use my simplification properties. Hey, I will distribute, we'll combine some like terms, and we can turn this into slope-intercept form. Okay, so the first thing I'm looking to do here is the next thing is, all right, I see a minus right here, so I'm going to turn that into a big plus. We need to know that. That's just a skill, that minus a negative number is addition. And then when I start to actually go to simplify, I'm going to multiply. I'm going to distribute. -1/2 times x is -1/2 x. Okay. Be careful here. -1/2. We got to treat this really like -22 is actually going to be +11. -1/2 times -22 is +11. And then we still have this y plus 1, but look what it's starting to shape up here a little bit. 1/2, like that's starting to look like slope-intercept form. The only thing we have left to do is get rid of this number here on the left side, right? If I subtract on the left, I got to do it on the right. So I end up with y equals -1/2 x plus 10. So that right there is the equation of the line, slope-intercept form, that has a slope of -1/2. Sure, -1/2, y equals mx plus b. This b we had to calculate. Right? That wasn't nowhere given to us. That wasn't on the paper. I didn't see it anywhere. I had to go through, and it wasn't an overly long process. It was kind of getting things where they go, but it's always the same two steps: distribute, and then bring over this number, whatever it is. All right, going back a little bit. Last one. So we're kind of leveling up again. I think this one's a little bit tougher as far as what we got to do, what I'm asking you to do. So the same initial setup is the same. Write the equation of the line in slope-intercept form that passes through these 2 points, -6, -10, and 9, 0. That's all we get. Oh no. So I still think we're going to want to use our point slope form. I know I wrote all over it here. I'll rewrite it down here. I still think we want to use that. That's going to be kind of our go-to, other than the one nice case where we're handed our y-intercept. So I think we want to use this. If I want to use this, though, what two things do I need? I need to know a slope, and I need to know a point on our line. Now, I think that second one we can actually, we have. We need to know just any random point on our line. Like the last problem, it was 22, -1. I actually know two random points on my line. I could pick either one of these. We can use either one. I'll pick maybe this first one. Why not? It doesn't matter. But we'll call this x1 and y1. And that's kind of the nice part about this form is I could use either one. Okay. So, all right, it's cool. That'll be our point. We'll use -6, -10 when it comes to this point. The issue that we're running into, or maybe that we're seeing, is we don't know the slope of this line. It's not 9, it's not 0. These are just random points on the line. So how are we going to find their slope? Well, this brings us to I don't know if I should say last, but it brings us to another formula that we should have seen quite a bit in algebra class, what we would call our slope formula. Holy cow. Whole slope formula. And again, we don't have to have this memorized. We just got to recognize when do I have to use it and kind of understand how to use it. So M equals, I know it's low on the board here, hopefully you can read it. M equals y2 minus y1. So the change in y's over the change in x's. That's a fancy way. It's a formula-based way of saying the rise, right? You change vertically, your vertical change, your rise or your fall, over your run. That's the phrase that everybody remembers when we start talking about slope, rise over run. This is just a kind of a formal way of calculating rise and run. All right, y2 minus y1 over x2 minus x1. So we got to use that. You need 2 points to use this, and that's exactly what we have. I've already called this one x1 and y1 because we said later on we're going to use it in our point slope form. So why not just call this x2? That's the x coordinate. And this is the second y coordinate. And then this way, we can plug all that stuff in to our slope formula. We'll get our slope, and then the rest will be very similar finish to how we finished the previous one. So let's do it. For our actual calculation here, slope equals m equals y2, which we're calling 0, minus, so same issue that we're seeing here, -10 over x2, which I've called 9, minus -6. So just watch. Remember, those are additions, so it's really +10 over +15. And with anything else like a fraction, we would always want to reduce that. 2 goes into the numerator, 5 goes into the numerator 2 times, and 5 goes into the denominator 3 times. So the equation, or I'm sorry, the slope of the line that we're looking for, or we're looking at, or we're talking about, has a slope of 2/3. That's a lot to do. I mean, that's a lot to remember. That's something we have to be able to calculate. From here, once I'm at this spot, we're essentially starting right where we started the last problem, where we have a slope, we have a point, right? That's kind of what we're up to right now. I have a slope, I have a point. I could use either one of these points we said. I'm just reiterating that. And I'm using my point slope form. So let's do it. Let's go through the last part of it here. I'm filling in everything I know. So I'm starting over here. Y, remember that y just stays kind of generic, minus, let's see, I'm calling this y1. So y minus -10 equals m, which we went through all that work to calculate, 2/3 times parenthesis, let's see here, x minus, what's my x1? -6. All right, so we've kind of got that double simplify going on here. I've got turn that into a big plus, turn this into a big plus. It's the same 2 steps now. Distribute, so 2/3 x, and then 2/3 times 6. Make sure we're using 2/3, like not 0.6 or not 0.67. 2/3 times 6 is exactly 4, +4. And then the last thing, am I going to have enough room to squeeze it in here? Subtract a 10 from both sides. I think I can squeeze it in. I don't want to clear anything. So the equation of our line, after I do the subtraction, we'll just jump all the way down to the bottom here. Just ran out of room, but y equals 2/3 x. 4 minus 10 is -6. There we go. We are in slope-intercept form of a line that passes through these 2 points. Wow, that's a review. So that's some of the skill stuff, and we covered quite a bit. We covered point-slope form. We covered the slope formula. We covered how to use each. We covered slope-intercept form, y-intercept. So there was a lot of algebra concepts that just came at you right there. Hopefully not for the first time. And that was just all review. So let's get into the new stuff. I think we can kind of jump over this. We talked what slope is. Vertical change, the vertical change, the rise over your run. We added our slope formula, so just make sure you have that slope formula in your notes. Remember, if we have a graph, we could count, if there's tick marks, count your rise, count your run. So, yeah, I think we're okay there. I'm actually going to jump here. So when we start talking about slopes in the coordinate plane, then there's really 4 situations that we could see. We could have I guess I probably would have started with positive, but we'll go in the order. A negative slope, we would say falls. Okay, and some of this is just recognition that if I see a line that's falling from left to right, we need to recognize, like, hey, that should have a negative slope, right? So like my rise would be down, over. I'm falling, actually. I'm going down and then over to the right. So a negative slope falls left to right. And if that's the case, then I would hopefully think that we could recognize that a positive slope rises from left to right. So we're talking about line K here in this case. Okay, it's kind of up and to the right, up and to the right. So that would, whatever that, I don't know exactly what it is, but I could tell you that this line K has a positive slope. The two kind of weird ones, and they're unique in the sense that a vertical line is undefined as far as slope goes. So let's just say an undefined slope would be a vertical line. We can say it like that. I don't know if that's exactly what we should have been talking about there, but vertical line has no slope. And even if we look back at our definition, the slope of a non-vertical line. So that's what it means by undefined, is a vertical line is not included in this definition. So undefined slope is a vertical line. Okay, and that's what we would say if I say, hey, here's a pink line, this line Y. What's the slope of that line? If it's a vertical line, we would say, don't say 0. That's something totally different. We would say undefined. That line has no slope. It's undefined. Even saying no slope isn't great because that might imply 0. It's undefined. The slope is undefined for that line. Then the last part, a 0 slope would be a line that is horizontal. All right, so our last one that we haven't talked about here, and I know there's a lot of lines on the page. I think this is the one we're talking about. Oh, no, it's actually down here. That's the x-axis. But it's, I almost said parallel. That was kind of the big reveal there, but I think we're getting there. A horizontal line has a 0 slope. All right, and even this one I screwed up. I did the y-axis when it should have been line N right here. Anyways, hopefully that's a quick, easy thing, rising and falling versus vertical and horizontal. Here actually is the big kind of reveal for us. All right, so let's add this to our notes. Why, we said this is a geometry, chapter 3, 4, 5, slopes of equations of lines. How does this fit with everything we've been doing? We're in chapter 3. The name of chapter 3 is parallel and perpendicular lines. Here's where it fits. Here's where it connects. Okay, so we've been talking parallel lines in the previous lessons. Parallel lines, what's the relationship between their slopes in a coordinate plane? So in a coordinate plane, 2 non-vertical lines are parallel if and only if only if they have the same identical slopes. which hopefully that's not a big reveal. And even that was something I believe is covered in Algebra 1 class, and it should be. Parallel lines, same slope. If this slope is, right, what are these positive or negative slopes? In this picture right here, I would say those should be, well, not should be, they are. They would have a negative slope. They're falling from left to right. But they would be the same. If they're marked as parallel, if I can see they're parallel, the slope of line 1 should be the slope of line 2. This also applies to vertical and horizontal lines. So, two horizontal lines would both have a slope of 0. All right, so they have the same slope. And even for vertical lines, because I know this says non-vertical lines, but vertical lines, if two lines both have slopes that are undefined, those vertical lines would be parallel. All right, so same slopes, that's the big takeaway. Parallel lines equals same slopes. Can make that connection. Perpendicular is a little bit different. Well, definitely different. Right? There's no way that they're the same. They're actually kind of going opposite directions, right? If I look here, this line has a negative slope. This line has a positive slope. But they're not the same steepness. This one is really steep as it's falling, and this one's kind of just slowly rising. So they're not just truly opposite numbers. There's two components that we have to talk about. So in a coordinate plane, two non-vertical lines are perpendicular if and only if their slopes are what we would call, maybe we've heard this phrase before, opposite. Let's write that out, opposite. Which does mean one's positive and negative. So opposite means different signs, a positive one and a negative one. But then also, they need to not only be opposite, but also reciprocals. What does that mean? We can be a little bit here informal, but maybe we'll do an example. Flipped, like flipped over. And we'll do an example here. I think that hopefully clarifies that. But you turn it over. 1 divided by, the fancy way would be till 1 over a number is the reciprocal of it. So for example, if two lines are perpendicular, slope 1 could be 2, okay, fine. But then the line that's perpendicular to it should have a slope that if 2 is positive, so this one needs to be negative. That's the opposite portion of it. But then I need to flip 2 over. How do I flip 2 over? I was going to try to flip the actual number, but remember 2 can be written as 2 over 1. The reciprocal of 2 over 1 is 1 over 2. So two things have to change. The sign from positive to negative, or it could be negative to positive, depending on what your initial line is. And I need to flip that line over. All right, so that's kind of the big review there. Also, just kind of side note, same thing, that if I say, hey, are these lines perpendicular? If we have a slope that's undefined, a vertical line, and a line that has a slope of 0, m equals 0 on this line, m, we wouldn't even really say, but m's slope is undefined for this line, that meets the criteria of being perpendicular as well. So that's kind of an exception to this rule right here, although we use the non-vertical lines in the definition, so I think we're not really making an exception, but just kind of making it a side note that vertical and horizontal lines are also perpendicular. All right, so that's kind of the big note. I would say we got a couple of things here. Most of the stuff we've talked, so this is kind of getting into the 3-5 right and graph. We talked slope-intercept form extensively on that warm-up. Y equals mx plus b, we got it. B is the y-intercept, m is the slope. Point slope form, again, we talked about, we used it extensively in those first two of the 3 first prerequisite checks, so we should be good there. The only one that we're going to see here a little bit is what's called standard form, okay, where I have really my x and y on the same side is what makes it standard form. So something like 5x minus 3y equals 30. I'm just kind of making up numbers there, but a, b, and c would be numbers. That's still a line. It's not in slope-intercept form. It's not in point-slope form. That's what's called standard form. So that's actually the next thing we'll look at here is a standard form. But what we have left is just applying all these principles. I know we did some examples kind of to start, although I would argue that those are more kind of review concepts for us. But we've got some examples. How do we apply all these concepts? All right. Okay, so the first thing, just again, this is more of a skills check. We could have probably did this early on as far as just a prerequisite check. I'm asking you to graph 2x plus 3y equals 6. Holy cow. And again, we haven't done that in a while, so let's walk through it and make sure we understand how to do this. I'm going to show two different methods. I think for a lot of us, how would I graph this? Well, first off, what form are we in here? That was the one we just got done talking about. That's our standard form, 2x plus 3y equals 6. The problem with this form, why it's not great for graphing, is none of those numbers are my slope and none of those numbers are my y-intercept. So just the way it's written right now, I can't just look at it and say, slope, y-intercept, I don't know. So for this first, right, option 1 that I'm giving us here, we'll do it right here, would be to identify your slope and your y-intercept. So take my original 2x plus 3y equals 6 and say, you know what? Standard form's okay for certain things. I don't like it, though. For graphing, I'd rather have this in slope-intercept form. So that's a fancy way of saying get your y by itself. So I'd subtract this term, move it to the other side of the equation, basically move everything away from the y. So now I'm sitting on 3y equals negative 2x plus 6. We're getting there. The y is almost by itself. There's still a 3. The common mistake is I need to divide this whole side, the right side, by 3, not just this part right here. I know 6 divides by 3 nicely, and that's the one that everybody wants to do because 6 divided by 3 is 2. But I can't pick and choose parts of a side of an equation. I need to divide the whole side by 3. So each term individually. So left side, all right, we've achieved our goal of getting the y by itself. And to be honest, it's not terrible. I don't have to divide this out and say like 0.67 or 0.6666 repeating. Let's leave it as negative 2 thirds x. And then if it does divide nicely, sure, let's do it. 6 divided by 3 is 2. So we've gone through a little bit of work there to turn this standard form equation into slope-intercept form. And the advantage to doing that is now I can look at this and say, oh, okay, hey, my slope is negative 2 thirds, and my y-intercept is the 0.02. Well, that's all well and good, but how does that help me graph it? Hopefully this part we remember. 0.2, right? I can look at this and see that's my y-intercept. 0.2, it's right there. How do I use the slope to help me graph? Remember, if we think of negative 2 thirds as a rise and a run, rise over run, it's actually telling me what to do. It's saying rise negative 2. So if I put my pen on the paper at my y-intercept and say rise negative 2, that actually means go down 2. Right? I'd be starting right here. I'm putting my pen on the paper. I'm going to go down 2, rise 2, fall 2. But then run, because the run is positive, I should be running to the right 3 units. Could we work it the other way? Could I go up 2? So I actually did rise 2, so that's positive 2. But then if I move left, that's negative 3. So that still applies because we're moving left. That's still a negative 2/3 slope. We connect our points, use arrows. There we go. We're graphed. I've identified my rise or my slope, my rise and my run, my y-intercept. So that's what we'd be doing for this first method. If I say that's what I want to do, tell me what your slope is, tell me what your y-intercept is. That would kind of be your work for that problem. The second option, and I know we have it graphed, so it's not the picture's not going to change or anything here, but just maybe giving us a second option. So starting over, method 2 here would be identify your x and y intercepts. And I kind of like this one for a standard form graph. So it may be worth hearing here. 2x plus 3y equals 6. And I say, all right, hey, you know what? Standard form actually is kind of nice to identify your x intercept and your y intercept. Now I know we already did it, and I know our y intercept is 2 from the previous work, but let's say I hadn't done any of this stuff yet. What's true about every x-intercept? Or let's actually start with the y-intercept. What's true about every y-intercept? Every y-intercept on the face of the Earth on a graph, on a coordinate plane, has an x coordinate of 0, 0 something. So what does that mean? Well, it means that if I substitute a 0 in for x, so essentially just kind of, what happens if a 0 goes in here? It would kill this term. 0 times 2 is 0. 0 goes in for x, and I solve for whatever's left. That's going to be my y-intercept. So 0 went in for x. Let's solve for y. What is it? We would divide. I'm talking through it. I'm not showing my work. I would be dividing by 3, divide by 3, divide by 3. 6 divided by 3 is 2. Do we follow what happened there? I essentially covered up this term here. That's what when I teach it in algebra, I call it the cover-up method. Cover up the term you don't want and solve for the remaining variable. Oh, sweet. Same exact process. Let's take this. Let's see if we can get this little green line out of here without screwing this whole thing up. All right. Oh, I had it. And we'll do the same thing. So for my x-intercept, what's true about every x-intercept? It has a y value of 0. Thought I was changing colors there. So I say, all right, well, if my y is 0, that kind of knocks that term out, and I solve for what's left. Divide both sides by 2, divide by 2. I get x equals 3. So I only end up finding 2 points, but to make a line, that's all you really need is 2 points. So I'd say, hey, let's put these on the graph. Where's the point 3, 0? 1, 2, 3 zeros right here. 0, 2 is right here, which, again, I know we already have the graph made. But then I connect them, and I end up with the exact same graph. So there's 2 methods there for you. It kind of depends on the form that you're presented in. A lot of times, standard form is nice to use this x-y-intercept method, just because the work isn't quite as much. Now, if I gave you a line that started like this, y equals negative 2/3 x plus 2, well, no way am I doing the x and y intercepts. I'm starting with that and just saying, hey, you know what? Y-intercept is 2, down 2 over 3, I'm done. Okay, so I'm giving you some options there as far as how we're going to graph. All right. Where's this all going? How does this help me out here? Here's the kind of the parallel perpendicular stuff. All right, so example 2. We've got a line, so let's read through it. We'll talk through it together. Line H passes through this point, 1, negative 2. Where is that? 1, negative 2 is down here. And then it also passes through the point 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So line H, why not? Let's just put that on here. Oh, I'm going to redo that. That's not very good. I'm doing... Okay, that's better. So there's line H. We have the graph. We might as well put it on there. Line H passes through 1, negative 2, and the point 5, 6. What we're being asked to do is graph the line that's perpendicular to this line. And it's not just any line, but it has to pass through the point 2, 1, 2, 3, 4, 5. So the line that we're being asked to draw that's perpendicular has to pass through this point. So the easy thing to do would just be like, oh, sweet, I'm done. Look at that, perpendicular. Well, that's no good because I'm asking for, give me 2 more points on this, what I'll do as the pink line, but I don't know if I could accurately identify any more points because I just kind of slapped that pink line on there, which wasn't a great option. Okay, so how are we going to do this? Right, I actually have to kind of calculate some points here or have a process. So here's what I would look to do. What was the big note we took about perpendicular lines? We said their slopes are opposite reciprocals. So I'm thinking if I can find the slope of line H, I can use, let's see, the slope of, we'll just call it the new line. It didn't give us a name, I don't think. The slope of line H and our new line should be opposite reciprocals. So could I use a slope formula here? Absolutely. y2 minus y1 over x2 minus x1. I'm going to say, you know what? I got a graph. I can count old school rise over run and figure out my slope that way. So I got to count from this point to this point, count vertically, right? Your rise comes first. Rise 1, 2, 3, 4, 5, 6, 7, 8. So I went up 8, so that should be a positive 8. Oops, I meant to change color here. And then that's over my run. So up 8 over run 1, 2, 3, 4. And they were both positive because I was moving up and I was moving to the right. So this line H has a slope of 8/4, which, like anything else, we would want to reduce, and that divides nicely. A slope of 2. Now I'm not using that for anything right now other than hopefully seeing that, okay, hey, you know what? If this one has a slope of 2 and my line that we're being asked to draw is perpendicular to this line, my line should have a slope of, let's see, opposite. So if this is 2 is positive, I got to make sure my number is negative. And then I got to flip it over. It's actually conveniently the one that we did for our example. 2 over 1 becomes 1 over 2. So my line has a slope of negative 1/2, and actually that's all we need, because now I have a starting spot. I can put my pen on the paper at this spot right here and say, okay, hey, I know my line, it passes through this point, and I can use my new rise of negative 1, so down 1, and then over 2 to get a new point, and then do it again, down 1, over 2, here's a new point. Could I go this way? Sure, up 1, over 2. So here's the actual line, and that's way more accurate than we originally just slapping a line on there. And hopefully at this point, it's just a matter of now counting. Okay, what are some of my options for points? I'm not saying you have to use any specific points. The only one I'm saying we can't use is this one right here, right? Because that was a freebie. So what's an example? We could say another point on this beautiful brown line would be 0, 1, 2, 3, 4, 5, 6. 0, 6 would be an example of a point that you could put and say, all right. Now again, I can only answer that if I do this accurately and make a good figure. Let's see this one here. What's this one? 1, 2, 3, 4. Right 4, up 1, 2, 3, 4. So 4, 4 would be an option. Those aren't the only two, obviously. We could say, what is this one for? 6, 1, 2, 3 would be an option. 6, 3. All right, so we have some options as far as other points on our line that we could name. So that's an example. All right, so now that's our first true geometry using perpendicular lines in a graph. Couple more. Writing equations, almost full circle here, how we started the class. So now it's write an equation. So these directions are very similar to the prerequisite skills. Write an equation, that's SI, stands for slope-intercept form of the line that passes through this point, okay, and is parallel to this line. So that's not my line. I can't just copy this down. But my line is parallel to that line. So we said, how do we write equations of lines? For the most part, I would say 90% of the time, we're using this, and I'll write it one more time, y minus y1 equals m times x minus x1. It's the most useful because it's a little bit more open-ended. What do we need to know to use this? We need to know a slope, and we need to know a point on our line. Okay, so we get that. We get the point on our line, kind of like that third example that we did in the warm-up, that we're passing through the point 1, negative 1. Like that for sure is a point on my line. 1, negative 1 is a point. So when it comes to it, we'll call that x1 and y1. Awesome. The only thing that we have a little issue with, just like that third one on the warm-up, was we don't know the slope. It didn't tell us like, hey, use this for your slope. But what else did it tell us? It told us the line that we're trying to write the equation of needs to be parallel to this line. And this one is very conveniently written in slope-intercept form, y equals mx plus b. The negative 1 here doesn't mean anything for us. The only thing I'm really looking at right now is, what is the slope of this line? And this line's 2. If I'm parallel to this line, my line has to have this exact same slope, so I should be using 2 for my slope. Does that make sense? That if we're parallel, so that it's just another way really of presenting, like, how can you find a slope? It could be told, here's a slope. We could say, here's 2 points. Use the slope formula, calculate the slope. Our new kind of option is to say, well, I'm not going to give you any of that. I'm going to say, here's a line. You're either parallel or perpendicular to it. Figure out what your slope should be. All right. So then from here, like we said at the beginning, it's now just getting everything where they go. Y minus y1. We've seen this a lot, that double minus. It's just the way it works out. It doesn't always go that way. And then m, which we figured out was 2 times x minus x1. All right, we've got big old plus there. Let's do our distributive property, 2x minus 2. And then last thing, we'd bring this 1 over here and say our equation, the line that it was asking us about, should have the equation y equals 2x. And just be careful here, that's negative 2 minus 1, which is negative 3. This line that I kind of erased or crossed off. And the one that we just came up with, so 2x minus 1 and 2x minus 3 would be parallel. They have the same slope, but obviously this one, they had some criteria that it had to pass through that point, so that's why we need to calculate that y-intercept. Let's do a perpendicular one, and then the last thing we have is some vertical horizontal lines, and then we'll call it. All right, so we've got a very similar setup. Write an equation of a line that passes through this point. All right, so we've got our, I'm just presetting this up because I know we're going to use it. Hopefully yours is just kind of traveling with you. You've written it down in the beginning. Let's see, if I want to use that, I need to know a point. Let's do it the same way. I need to know a slope, and I need to know a point. So it's telling us our line J, passes through this point. Cool. That's one of the two things I need to know. We'll call that x1. We'll call that y1. And it's got to be, just pay attention though, little things. It's now perpendicular to this line. So I don't want to use -3. Like -3 is the slope of that line for sure. If our setup said parallel, then 100% I would use -3. But because it told us we need to be perpendicular to this line, I need to make sure that my line, if this is negative, mine should be positive. I can put a little positive if I want. And I need to flip that 3 over. So it becomes 1/3. It's positive 1/3. You don't have to have the positive there, but maybe it doesn't hurt to remind us. I've seen people just leave it as negative, and all of a sudden everything else is wrong. All right, so I've used this line to help me come up with my slope. All right, let's finish it. Maybe the fourth time today that we're going through this process. Y minus y1 equals m. I'll just use 1/3 times x. That's generic x minus x1. All right, little distributive property. 1/3 x. And again, just watch your signs here. It's -1. 1/3 times 3 is 1. And then last but not least, as always, we're going to bring over whatever numbers hanging out here with the y and say that y equals 1/3 x plus 1. So the numbers are kind of small here just to kind of keep things easy, but 1/3 x plus 1, yeah, whatever. I guess it doesn't matter if the numbers are big or small, whatever. 1/3 x plus 1 would be perpendicular to this line and also pass through that point. All right. Last example here. We talked, I know we mentioned earlier, parallel, perpendicular lines, vertical, horizontal lines. What do we do, in a situation when it's asking us about lines parallel, perpendicular? So there's some stuff going on here that I think may need a separate review page here. So just bear with me for a second. I know I said last thing, but I don't know how many of us remember this. Horizontal. Let's just a heading here. I would add this to your notes because, like I said, I don't know how many of us are going to remember this. Equations of vertical and horizontal lines. Okay, let's pause it, get your heading set up there. So let's start with vertical, just because that's what we wrote first. Now, just because it has a slope that's undefined doesn't mean like we can't work with them and talk about equations of vertical lines. Here's the deal. Every vertical line takes the form x equals something. X equals some number. Takes the form x equals something. So for example, the equation x equals 2, well, it doesn't matter, any number, x equals 2, when I see that, it's like, wait, what? Graph that line, x equals 2? What the heck are you talking about? And I know we're just being kind of low-key, not super formal here, but what is the x equal 2? What does that even look like? Is it a point? So on the x-axis, right, that's where 2 would be, 1, 2. It's not just a point right there. It's actually a vertical line passing through that point 2, 0. So this line right here has the equation x equals 2. Whoops, that's an x, not y, x equals 2. So that's just something we need to know. Like that's, okay, vertical lines are x equals something. And hopefully, all right, well, if vertical takes on that form, horizontal, just abbreviate there, takes on the form y equals something, some number. All right, we'll do the same thing. Why not? We're here. We're making our notes. So the example could be y equals -7. Just making up any number. And I say, hey, graph that. Well, we need to be down here at 1, 2, 3, 4, 5, 6, 7. I need to have, it's supposed to be a little bit lower, a horizontal line. Let's see if I can adjust it. There we go. Look at that. Magic. This horizontal line has the equation y equals 7. So they're meant to be, like simpler. It is. There's no x. Like they either have an x or a y. So they are definitely simpler equations. But I know because they're a little bit more obscure, they don't come up as often. We're probably a lot more familiar with y equals mx plus b than we are just y equals -7 or x equals 2. Okay. So that's a little bit of background on how we're going to look at the last example here. So it's a very similar setup to stuff we've seen. The wording says it's asking us to write an equation of a line that passes through this point. Okay, we've heard that 3, 4, 5, 6 times today already. So the equation we're about to write, it has to pass through this point, and it's got to be parallel. Okay, same slope to the line y equals -8. Now, I'm guessing had we not reviewed what we just did, I don't know how many of us would have looked at it and said, what? Equation line y equals -8. So something you can do here, and I know we didn't do it for the other ones, but would be to make just a really just simple graph, right? I'm not making tick marks other than maybe I don't even know if I have to make tick marks. Where would the line y equals -8 be? It'd be down here somewhere, right? That's y equals -8. Okay. And the reason I'm making just a really informal graph is it gives me a visual representation of what's going on. Now, again, I need to know that a horizontal line has that equation, y equals anything. So now our line that we're being asked to write the equation of has to go through this point, 1, 2, 3, 2 right here. And again, I don't know if I have to be super detailed, but I think it's maybe helpful to put the point, at least the coordinates of that point right there, 3, 2, and say, all right, if we're parallel, we all know what that looks like. Hey, it's got to be another horizontal line. It's going to be y equals something. If this is y equals -8, this has got to be y equals something. What is my equation? Y equals what? And I'm actually going to look, okay, what is the y coordinate of all the points that are on this line right here? 0, 2, 3, 2, 1, 2, 2, 2. All the y's are equal to 2. So I'm not trying to make it harder than it is. These numbers are showing up here, but what people do is say y equals 3 or x equals 2, x equals 3, right? Those are kind of your 4 options as far as, okay, if I'm going to be parallel to this line without seeing it, sometimes people make that mistake and say y equals 3, x equals 2, x equals 3. Right, so just do a quick visual. I think that's probably the easiest way to do it. Last one, let's do a perpendicular one. Similar setup, equation of line passes through this point and is perpendicular to this line. So we're actually using the same line. So let's see, y equals -8 would be, again, down here somewhere. Y equals -8. Our line that's kind of in question that we're being asked to write about is -5, 6. And again, I don't even need tick marks. I can just call that, hey, -5. As long as I know, -5, 6 would be over here. We'd go left 5, right, left 5, up 6, okay? And how do we relate to this pink line right here? Well, the line that we're talking about needs to be perpendicular. So we should end up with actually a line that looks like this. So we kind of have what it looks like, perpendicular right there, right? What is the equation of this vertical line? Now, obviously, we could flip back and look. Oh, hey, vertical lines look like this. But remember, vertical lines all take on the form x equals, and as long as I kind of know that, I think it takes some of the guesswork out. What's the x coordinate here? X equals -5. And that's not a coincidence. Like this -5 in turn is telling me that -5. I'm just trying to give us some options, and so we're not guessing. Okay, make a quick little picture. Doesn't have to be detailed. See what's going on. Parallel, perpendicular. So that's my my suggestion for how we're going to deal with parallel or perpendicular lines in equations. Okay. Oh, wow. So there we go. There we have it. That's a review. I mean, it's almost a review lesson. It's connecting stuff that hopefully you talked about, you learned about in an algebra class, writing equations of lines, graphing lines, slopes, to the concepts that we're talking about in geometry class about being parallel, perpendicular. Okay, so we've definitely, I think we've hit all our goals here as far as we've compared, we've found slopes, we've compared them, graph lines using their slopes, using x-intercepts, y-intercepts, and then we've written equations of lines parallel and perpendicular to other lines. Totally, we killed it. So there we go. We are officially done. Lesson 3, 4, 5 is in the books. Let's call it. I will see you in future lessons.